My name is Michael Pont. In this short video, I'm going to discuss ways in which we can improve confidence in the safety of advanced driver assistance and autonomous vehicle designs that incorporate unqualified software or hardware components. The examples I'm going to discuss will be intended to achieve compliance with the international safety standard ISO 26262. So in this presentation, I'm going to begin by discussing very briefly the techniques that are sometimes used to develop a general purpose embedded system. I'm then going to consider the development of a safety related ADAS, Advanced Driver Assistance, or AV, autonomous vehicle design. I'm going to consider how we can address the project constraints by separating the system functionality and the safety functionality in the system. And I'll then present the conclusions. So let's begin by considering how we can develop a general purpose embedded system. This is a typical approach that many organizations follow. They have a standard off-the-shelf processor, a QM processor, quality managed processor. They have some driver code, they have perhaps a real-time operating system, and then there's code that's developed by your organization on top of this platform. I'm assuming that if you're watching this video, you have some familiarity with the process of developing such a general purpose embedded system. So, what happens then if we want to build a safety related ADAS or AV design? Many organizations, I think, follow what appears to be the obvious option here. So rather than having a QM processor, we now have an ASIL D processor in this particular example. So this has the highest safety rating that's recognized in the ISO 26262 standard. We assume we have some driver code for interacting with that processor, and we assume that driver code is also ASIL D. We assume that we've got a real-time operating system that's also ASIL D, and we assume that you'll create your code to run on this platform, and you'll also do that according to ASIL D standards. This may look straightforward, but moving to ASIL D in this way is not quite as easy as it looks for most organizations. Let's just take the processor, for example. Formally, in terms of ISO 26262, this is a safety element out of context, an SEOOC, and it will be provided with a safety manual that defines certain assumptions, conditions of use, etc. So when it comes to using this kind of safety element with the safety manual, we begin immediately to face classic systems engineering challenges. Typically, not all of the components that we'd wish to use are qualified, and even when we have qualified components, there are gaps between the components. It's not always clear how we're going to glue this whole system together. Let's just stick with the processor for a minute. One of the questions and one of the ways that people sometimes trying to deal with some of these challenges is to say, okay, do we actually have to use qualified hardware in our design? Do all of the components, all of the transceivers, all of the components on the PCB, do these all have to be qualified? And some people suggest, well, there are designs out there that clearly don't have qualified components in them. For example, the International Safety Standard IEC 61508 predates ISO 26262 by many years. And there are many SIL 3 IEC 61508 designs on the market that are based on unqualified microcontrollers. SIL 3 in IEC 61508 is essentially equivalent to ASIL D in ISO 26262. So these designs are based on unqualified microcontrollers. When many of these designs were created, there was no practical alternative. There were no ASIL D microcontrollers available, and custom microcontrollers were common in aerospace at this time, were very expensive, impractically expensive for these kind of applications. It couldn't reasonably be expected that someone would use such a microcontroller in a ASIL D design. The world is now a different place. There are various ASIL D and ASIL D processors available. Starting a new design with an unqualified microcontroller may be very difficult to justify in court for IEC 61508, ISO 26262 and related projects. The bottom line is it's almost always necessary these days to use qualified hardware components in your design. But there are other constraints here as well that also need to be considered. This is a fairly typical list that we find when we talk to organizations. People building a project tend to find that there are hardware and software components that they want to use are not all qualified. There may be gaps between the qualified components. The safety standards are complicated. The development team may lack safety experience. The management team may lack safety experience. There are usually often very severe time to market concerns. There are usually project cost concerns, and there are usually unit cost concerns. Somehow or other, we've got to create our safety-related ASIL D design in the face of these significant constraints. So I'm going to suggest that rather than trying to build this whole system up from the ground up to be completely compliant with ASIL D, there's another option. International Safety Standard ISO 26262 allows us to perform what's usually called an ASIL decomposition. What this means in practice is that we are permitted, in compliance with this standard, to divide the design into two independent elements. These elements can be seen as providing system functionality and safety functionality. For the system functionality, we can develop this using QM components, using the approaches we've looked at earlier. For the safety functionality, here we do need to use qualified hardware, and when we are achieving these requirements, we use what's known as TT wrapper software. I'll say a little bit more about that shortly. So let's just look at what this actually means then. So we're going to perform an ASIL decomposition. We start with a certain set of functional safety requirements, and I'll assume those functional safety requirements are at ASIL D. We're going to split this then into a set of requirements, not safety requirements, simply requirements. These are QMD in ISO 26262 terms. So here we have the QM part of our system based on a QM processor running your conventional real-time operating system, if that's what you're going to use, your conventional driver code, and your code on the top. So this code is not safety related. On the other hand, we're now adding all of our functional safety requirements are being allocated to an independent safety monitoring system. All of the safety responsibilities are allocated to this monitoring unit. None of the safety responsibilities are allocated to the QM component. People sometimes think that the way they might be able to address some of these challenges would be to take the QM processor and to allocate the functional safety requirements to a conventional watchdog timer that might already be incorporated into the QM processor. This is simply not adequate in almost all cases. A conventional watchdog timer provides insufficient diagnostic coverage to allow us to meet safety requirements in this kind of system. The alternative that we employ involves use of what's known as a TT wrapper. I'll say a little bit more about that in the next few slides, but essentially this is a very simple monitoring element, usually implemented on a separate processor, that's used in combination with your QM components in your system. Our TT wrapper is based on a TT software architecture. Very briefly, a TT software architecture is usually a bare metal software platform. That is, there's no RTOS, no Linux, no Windows. We have one active interrupt per CPU linked to a periodic timer tick as our starting point, and all peripherals in the design are pulled. This may sound like a very simple architecture, perhaps too simple if you're used to using a conventional RTOS and event-triggered systems. The key point of building the architecture, building our system in this way, is that this very simple architecture provides two very significant benefits. We can model the system behavior precisely at design time, and we can detect changes to the system behavior at runtime. You'll find an introductory video on TT systems on our website at the URL shown, if you're interested in exploring this any further. Once we have the ability to create software using a TT architecture, we can then move on to create a TT wrapper for use in our application. So a TT wrapper is usually based, in this case, on an ASIL D processor platform. On this processor platform, we'll have some driver code as before. In place of the operating system, we'll have a customized, very small TT task scheduler with related safety monitoring components. On top of this, we'll run the task code for the application. So there's a small amount of task code to be created on top of this framework. The typical software architecture used is illustrated on the right hand side of this slide. This is called a correlator B platform. It incorporates various monitoring systems along with the simple task scheduler, and is designed to give us extremely deterministic timing behavior and an ability to monitor the system and detect even very small changes in the system behavior at runtime, which is exactly what we require in this kind of monitoring system. So once we incorporate our TT wrapper into our system, it looks like this. So we have our QM components on the left, we have our simple TT wrapper monitoring system on the right. Because the system is simple, we're achieving one of the other requirements or expectations in ISO 26262, which is that the safety mechanism will have a lower complexity and lower size than the intended functionality. And that is one of the things that we achieve with the TT wrapper in this design. So let's look at two simple examples of the ways in which a TT wrapper can be employed in a safety-related advanced driver assistance or autonomous vehicle design. Suppose we have a level 3, level 4 system which is semi-autonomous, in that sometimes this vehicle will be expected to drive itself. On other occasions it will expect to be able to hand back control to the driver. So let's further assume that we're going to use an off-the-shelf camera module, which I'm going to assume is QM rated, to determine whether the driver is alert and ready to take back control of the vehicle. This is clearly a very important consideration. If the autonomous vehicle has been driving, let's say, for 2 hours up a motorway, the driver may be asleep, or may be reading, or may simply not be paying sufficient attention in the design to take back control of the vehicle. He or she may even be ill So I'm assuming here that we're going to use a COTS camera module to determine whether the driver is alert and ready to take back control. Because this camera module is not fully safety qualified, it's just QM, we're going to take the data from the camera module, the raw image data, and we're going to feed it to a TT wrapper. And the TT wrapper here will be responsible for performing appropriate sanity checks on the data coming from the camera module and allows us to have greater confidence that the camera module is operating correctly. For example, the kind of checks that might be performed here is that the TT wrapper would be looking for small changes in the image between frames in order to detect that the camera module was operating correctly. Let's look at another example. Suppose we have, in this case, an autonomous road vehicle controller. So this time we've got the full control system for our vehicle that's taking information from the different sensor inputs, for example a LiDAR, a radar, image sensors in our vehicle, feeding those in and making a decision about the speed and direction of the vehicle. So let's assume as well that this component is also not fully safety qualified. It may have unqualified hardware elements in it. Some of these may be complicated, high power, off-the-shelf processor platforms that are not fully safety qualified. So this time we're going to feed the information from our ARV controller again into our TT wrapper. In this case, rather than simply performing sanity checks on the controller outputs, we're assuming that the TT wrapper is responsible for performing tests on the operation of the QM controller during the system operation. So typically we might expect that for every frame of data sent from the QM controller, between each frame the TT wrapper will perform a test on the system using the software architecture that we dealt with previously. So the TT wrapper is responsible for performing sanity checks on the outputs of the ARV controller and also for performing a continuous set of tests on that controller to ensure that it's operating correctly. And the end result of this process is that we get confirmed speed and direction information from the ARV controller that has been filtered by the TT wrapper and in which we can have greater confidence at the end of the process. So that brings us to our conclusion. What I've tried to demonstrate in this short presentation is that many ADAS and AV projects face constraints such as the fact that the available hardware and software components are not all qualified. There may be gaps between the qualified components. The safety standards that the development team have to comply with are complicated. The development team may have limited experience. The management team may have limited experience with safety-related projects. There are almost always time to market constraints in the system, and there are almost always constraints on the project cost and the unit cost of the system. We can try and develop an entire ADAS AV design from the ground up to be completely safety related, but what I've proposed in this presentation is that it may be more appropriate, certainly for the first product release, to consider splitting the system functionality from the safety functionality in the system. And I've suggested that this provides a practical means of meeting the above constraints for many organizations, particularly for a first product release. I've also suggested that TT wrappers provide a highly effective means of implementing the required independent safety functionality. This can be done quickly and very cost effectively. For further information about safety wrappers, please refer to our website. Thank you very much for watching this video.